Ladies and gentlemen, boys and girls, welcome back to another video. I hope that you all have been enjoying our little video lectures. Seems like we have to do pretty often. Today we're going to be doing numeric integration, and this is because I'm going to be out of town this weekend. Here we are, no class on Monday. So numeric integration, right? What is the deal with this? The idea is that, we've got, this curve here, and we want to estimate the area under axis. So we want to estimate this area under the curve, and normally what would we do? Well, this is going to be the integral from a to b of f of x. Okay. So then why would we ever try to use like numeric integration? Because really in practice, like if you're, in the real world, you're an engineer, what are you going to be doing? To find this area, you're going to be doing numeric. Now it's going to be on a computer, you're not actually going to be doing it yourself, but this is going to be how your computer does it, right? If you ever look up an integral, like, integral from 2 to 4 of blah, 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 dx, your computer's going to do these numeric strategies. And the reason is because antiderivatives are super, super complicated to compute, right? So you've been doing these explicit computations, like integral sine of x, integral sine to the fifth of x, cosine third, you know what I mean? We've been doing stuff like this. But really, in practice, that is going to be pretty uncommon. Most of the time, if I gave you something like the integral of ln square root x squared plus 1, divided by x to the third over 2, you have no idea how to. There's no good u sub. There's no good, you're cooked, right? And so what can we do? Well, we do know what this inside function is. And we can apply. You can put stuff in here. We can say, if this is f, we can do like f of 2 or f of 8, or we can put stuff in this. Right? So the way that we want to estimate these areas under the curve is we're going to do like Riemann sums. Right? So our normal Riemann sum, right, is going to be something like, we would have like the area, right, is going to be like the sum I equals 1 to n of f of xi delta x. This is our Riemann sum. And this guy's going to converge pretty well, and it's going to give us kind of what we have. We take more data points, and then now we're going to be doing, if we've got this guy here, we're going to be doing like these rectangles. Okay, well, but you know what I mean, right? We're going to be doing these rectangles. And so is there a better way to do this is the question. Right? Can we do better than this? Because, if you're doing numeric integration, you don't care just about the limit, right? Here in the limit, this converges honest to goodness to the integral. This converges and we're fine. It doesn't matter how, oh man, like when you're taking 7 n's, these are really big error terms. This sucks, right? And so you're like unhappy about that. But when you take the limit, it doesn't matter. In numeric integration, because we actually are going to be doing a finite sum of these, maybe n is going to be, if you're in your computer, right, you're only taking 1,000,000 rectangles or something like this. You're not taking an infinite amount of rectangles. Well, then there's going to be some kind of error. So we really are more inclined to minimize error than to just get a nice, easy formed. Like this is very easy to look at. Just f times the width, right? This is not rocket science. But if we can do a little bit better and make this maybe a little more complicated, for a human to look at, like, oh, this is kind of more complicated of a formula, this will still possibly give us a better error, which the computer likes. The computer doesn't care how it looks, right? A computer can put whatever function you put here, and it's fine with it. It's not going to be like, oh, it doesn't, I don't know how to do, I don't like fractions or square roots or negatives or whatever. The computer's fine with all that. It doesn't matter. So what do? Well, we're going to do the trapezoid rule. Trapezoid, right? So trapezoid rule. So the idea with this now is instead of doing boxes like this, we're going to take this point, and we're going to make a trapezoid. Right? Oh, and this looks much better, doesn't it? Now, there's still a little bit of error. Don't get me wrong, right? There's like, a little bit of error here and stuff, but like these secant lines, right? We're basically making these secant lines. This is hype, right? I'm happy with this. Hey, this is good. This is a good deal. So these errors are going to be much better than the normal Riemann sum rectangle. And so if we notice each one of these, well, so like A1, like this first trapezoid is going to be f of your first point plus f of your second point divided by 2, right? Like this guy here is going to be, it's like your slope, right? Slope form. You're going to have this guy divided by 2. So really, we're basically doing like this, right? We've got this average of, it's going to be our height. So we are averaging our two heights instead of just taking, if we've got this guy here and we're doing our normal rectangles, we're taking one representative. You are the representative of this whole area, and you are the representative of this whole area. Instead of doing that, now what we're doing is we're going to instead say that there's two representatives, and you take the average of them, right? So if you take, you've got this guy, you are the representatives of your area. So really, it's going to be something like. And so we shoot this middle, we get a little bit better of a representation of our points there. So it's kind of like, if you were to take one representative of the United States government, right, you're either going to get a Republican or a Democrat, which is going to be super unfaithful to the makeup of the government. But if you were to take two, right, maybe, well, then you're going to have Republican and Democrat, and you had to take their average, and this is more representative, right? So we're going to go ahead and average these guys. So this is going to be our trapezoid. And so for any of them, this is going to be kind of how we're going to have this guy plus this guy, and then, AN, any general N, is going to be F of the previous one, N minus 1. Sorry, let me make sure that I'm writing this, because this is actually XN minus 1. Writing with a mouse is very hard. Plus F of XN over 2 delta X. And so then if we add up all of these ANs, we've got A1 plus A2 plus ... plus AN. Well, then this now is going to be I can factor out a 1/2 delta X, right? These all have 1/2 delta X. So let me factor that out. 1/2 delta X. And then now we're going to factor. We're going to have F of X naught plus F of X1 plus A2, F of X1 plus F of X2 plus A3 ... plus AN. F of Xn minus 1 plus F of Xn. Right. And if you notice, we've got two F of X1s here, two F of X2s, two F of X3s, two F of Xn minus 1s, and then one F of X. Right? Because the F of Xn minus 1, if we did F of Xn minus 2, or the A of Xn minus 2 be F of Xn minus 2 plus F of Xn minus 1, right? This is like A n minus 1. And so then this guy will match up with this guy, so you get two of them. So the idea here, right, is going to be that the trapezoid, here, our area is going to be 1/2 delta X times F of X naught plus 2 F of X1 plus 2 F of X2, and so on, plus ... plus 2 F of Xn minus 1, and then plus just 1 F of Xn here. Right? And if you're looking at this shape here, this guy's getting double counted for this rectangle and this rectangle. This guy's getting double counted for this rectangle and this rectangle. This guy's getting double counted for this rectangle and this rectangle. So the only points that aren't double counted are going to be your Xn, or X0, sorry, and your Xn. These are the only ones that aren't double counted. Okay, perfect. So now that we've gotten this, yeah. So we're going to have... So we should be in here. Then our trapezoid rule, honest to goodness, is going to be T A B of N, right? So T A B of N, A and B are where you're going from, and then N is how many points you're getting. So how many examples you're doing. So, if I partition like 1, 2, 3, 4, 5, 6, well, then n here would be, it'd be 7, right? So we've got 1, 2, 3, 4, 5, 6, and then 7 would be the last one. So here, this would be like n equals 7. But the more partitions you take, the higher the n is. Okay. So here we are. This formula here, I am going to write as follows. This is going to be 1/2 h, and we'll write what h is, times f of x naught plus 2f of x1, exactly what I just, plus dot, 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 plus 2f of x and minus 1 plus f of xn. You'd think that after all these video games I've played, wasting my time, my mouse work would be a little better. But I suppose not. Alrighty. Here, h is going to be equal to b minus a over n. So just in the Riemann sum case, we're just taking h to be a, evenly partitioning spread of this function. Right, so if I'm here and I'm evenly partitioning these guys, well then if this whole thing is b minus a, each of these is going to be b minus a divided by n. Now these are obviously not evenly partitioned, but that's how you're going to do it. At this stage, I'd be saying any questions, but since we're not on campus, then I won't be saying. Okay, so we've got this error estimate, which is cool or whatever. This is actually the real meat and potatoes of what we're doing, but I'm not going to actually prove it, so it's kind of like, why are we talking about in a sense? Error estimate for trapezoid. Here we're going to say that the integral from a to b, f of x dx, can only differ by our trapezoid difference. So this absolute value of their difference is going to be how much they can differ. Right? So how far away are they? And we can bound this by this kappa times b minus a cubed divided by 12n squared. Wonderful. You're saying, what is kappa? Well, kappa here is going to be the max over the interval of the absolute value of f double prime. Okay, so let's parse this for a second because this is kind of confusing. So we've got a difference here on the right side, on the left side. So what does this say? This is saying that this is the most off the trapezoid rule can be. Right? So in other words, when you go ahead and you do all your trapezoids here, the most off that this error that you're having here can be when you sum them all up. So you do all your green all around the whole thing, the most that can be, because the integral is going to be actually, honest to goodness, the area under the curve, right? So if you're subtracting off this TB, this TAB of n, and you're taking an absolute value, so it's not signed. So anything up on top of here is going to be the same error here as down here. So if you had a bunch of bottom error, that's going to be equivalent, it's the absolute value. So we're saying how big can this error be? Okay, so it's going to be b minus a cubed, so we've got the length of our interval cubed, divided by 12n squared. So we're going to say that it's going to depend on the length of our interval, in a cubic fashion, and it's going to inversely depend on the amount of n that we're taking. So as n is getting really, really big, this error is becoming really, really small, which is great news for us. And if you notice, b minus a is never changing as we're taking n bigger. So really this guy, as n goes to infinity, which is great news. This is what we want. And actually the reason that we're doing this trapezoid rule is that this convergence to 0 is quicker than the rectangular case. So kappa here is going to be the max of the second derivative. So the most concave. So kappa is just saying as concave as f gets. Right? Because when f is the most concave, like at this point here, our trapezoids are going to have the most error. Sorry, this was a pretty bad trapezoid. But when it's like this, right? Because in a rectangle situation, right? In a rectangle situation, we're doing Riemann sums. really any difference, any variance is going to give us bad rectangle situation. This bad error here is going to be coming whenever we are not constant. So really, this kappa term in a Riemann sum would be something akin to the max of the first derivative, right? As changing as we can. Conversely, here we actually notice that if we're doing trapezoid rule, a line actually gives us no error, right? Because we're here, and we're just like this, and we're here, and we're just like this, right? So actually, changing, a derivative, like if it was just a line that's gonna have a constant derivative, that actually doesn't cost us anything in the trapezoid rule, but concavity does, right? When we're super concave, right? So imagine we were super concave like this or something. Well, then our trapezoids are gonna be, we're gonna have to make these like super long trapezoids. We're losing a lot here. So that's what this kappa is saying. We're factoring that. I hope I didn't waste too much time kind of going into that little spiel, but I like that. I like when we have these new formulas, looking at what they say, kind of what these terms are contributing. Okay. Cool, so we can do an example. I don't really want to, but I feel like I probably should. Yeah, we'll do an example. And I'm going to delete this all because, you guys have this in the video. So let's get into business. Here we're going to have an example. We're going to have the integral from 0 to 4 of, is something wrong with my mouse sensor? That might be what it is. This mouse is old, man. I've been using this thing for a minute. Actually, I got this recently. They used to have a wired version of the same one, laser Death Adder. Used to have the 20, like the Death Adder 2013. I got that back in like 2015. That was a good mouse, man. Back when I was playing Counter-Strike, I was like, oh, what does Kenny S use? I got it. All right, use trapezoid rule. With n equals 5. Okay. So we're going to use our trapezoid rule with n equals 5. We're going to make this chart. So this is going to be a big thing. So first off, let's get h is going to be b minus a over n, which is going to be 4 minus 0 over 5, which is 4/5. Okay. So let's go ahead and make our chart. xk here. And f of xk. So when k is 0, or when k is 1, when k is 2, when it's 3, when it's 4, and then when it's 5, like this is just, what number we're on, what step we're on. xk is going to be what? Well, xk is initially going to start at 0, and then it's going to go to 4/5, and it's going to go to 8/5, it's going to go to 12/5, then it's going to go to 16/5. And then it's going to go to 2. Am I tripping? Whoa, I'm definitely tripping. 25th is 4. Okay, that was my issue. I was about to say. Whoopsie. Okay. So we're going from 0 to 4 successfully. I'm happy with this. And now we just need to evaluate our function. So what is e to the negative 0 squared? What is e to the negative 1, or rather 4/5 squared? E to the negative 4/5 squared. E to the negative 8/5 squared. And dot, okay, e to the negative 12/5 squared. E to the negative 16/5 squared. E to the negative 4 squared, which is just 16, right? Cool. And so now what do? Well, we just need to go ahead and do our formula, right? So let me erase some more of this. And we're just going to say that t here, t 0 to 4 of 5, right? So we're going from 0 to 4, and our n is 5 here. This is going to be 1/2 times h, it's 4/5, times And now we just do these guys here, remember? And we got a 2 coefficient on the middle one. So 1 plus 2e to the negative 4/5 squared, which is just 16/25. Negative 16/25 plus 2e to the negative 64/25 plus 2e to the negative 140 plus 2e to the negative 256/25 plus 1 e to the negative 16, right? You gotta remember our e to the negative 16 is just gonna be the endpoint. It's not getting double counted. Okay, and then this is gonna be 0.888. About. Cool. Let's go ahead and bound the error. This is going to be the error function that we're going to be using, right? So let's go ahead and bound the error. So error is going to be less than or equal to, we said, kappa times b minus a, which is 4 minus 0, so 4 cubed, over 12n squared. And what is n here? It's 5, right? So it's 5 squared is 25, right? So this is going to be our kappa. So now once we find kappa, we're done. So what is kappa going to be? Well, kappa is the max of the second derivative. How do you find the max of a second derivative? Well, we got to go ahead and take a derivative of it, right? So we have to take 3 derivatives, fortunately. So I'm going to not bore us with the details, but the third derivative of f1, 2, 3 of x is going to be 4e to the negative x squared times x times negative 2x squared, plus 3. If you were to compute this, is what you would get. Okay. So for this guy to be equal to 0, then we have x equals 0, comma, plus or minus root 3 over. If you guys are confused about this, what are we doing? Well, just take f as f double prime. This guy's g. We need to maximize g. How do we maximize g? G prime of x equals something. Set this equal to 0. G prime of x equals 0. Right? This is exactly what we're doing. So we're just calling g f double prime. So then g prime is f triple prime, right? But just maximize this like you do in Calc 1. Okay. When we go ahead and plug these things in, we end up getting that f double prime. We end up getting that f double prime of 0 equals negative 2, and then we have that f double prime of root 3 over 2 is going to be bounded by 0 and less than 2, and similarly 0 is less than or equal to f double prime of negative root 3 over 2. Same thing. We also have to check 4. Negative root 3 over 2 is less than 2, and then we have to check our endpoints. So f of... Okay, so basically the idea here is that we end up getting that f of 0 is going to be our maximizing. So that means that our maximum from over 0 to 4, right? We've checked our critical points, 0, root 3 over 2, negative root 3 over 2. And you go ahead and check these on your own if you don't believe me. And we've also checked our endpoints, 0 and 4, which 0 is actually a critical point. So we end up getting that the maximum of this... sorry, this should not be a double bar. The maximum of this absolute value here is going to just be 2, right? And all these guys are bounded by it. This means that E is going to be less than or equal to 2 times 4 over 12 times 25, which is something like 0.43. Right, so we know that with this 0.888 that we've gotten, the actual estimate, right? So the actual area is going to be between 0.888 minus 0.43 is going to be the actual area. And then this bounded from above, 0.888 plus 0.43. Right, so it's going to lie somewhere between those. Okay. Cool. That's a nice little example that we've done here. This video is getting kind of long. I don't expect it to be this long. Let's go ahead and delete stuff here, and then maybe we can look to Simpson's rule. Okay. Simpson's rule. I'm not going to bore you too much with the details. Simpson's rule. Same as trapezoid, but using parabolas instead of trapezoid. Right, okay, so let's think about this for a second. In Riemann sums, we're taking one representative. Boom. In trapezoid rule, we're taking two representatives. Boom, boom. In Simpson's rule, we're taking three representatives. Boom, boom, and their midpoint. We're making this parabola. That's the whole idea. So then, what do we think? If you're at a part that is a parabola, right? Okay, we're at a parabola here. We take these three representatives. Well, then look, it's concave, but it actually is followed perfectly. Just the same way that trapezoid rule, if we're on a straight line, it's following it perfectly. So then what do we think our kappa is going to have to deal with here? Oh, kappa is going to have to deal with the third derivative, right? Or the fourth derivative, right? I can't. So I'll give you the formula. It is the exact same thing. You just do your, this guy over 3, right? If you guys it's in the textbook if you guys want to look it up. But I'm just going to give you the formula because we've done all this stuff on trapezoid, and it's the exact same thing. I'll be honest with you. Okay. So the integral a to b f of x dx is going to be something like s for Simpson. B of n is going to be h over 3 f of x naught, right, because we're not double counting this, plus 4 f of x1 plus 2 f of x2, right, because this guy's getting counted by this one and this one and this one. 2 f of x2 plus 4 f of x3, we're alternating here, plus 2 f of x4 plus ... plus 2 f of xn minus 2 plus 4 f of xn minus 1 plus f of xn. And this is all multiplied here by h over 3. H, once again, is going to be b minus a over n. This is your delta x. Simpson's rule. N must be even. Very important. Because that's how this 2, 4, 2, 4 all works out nicely, right? If that's not the case, then you're cooked. So please make sure that your n is even. Which it'll tell you, right? And this is not that big of a deal for you, I suppose, because when you do these problems, it's going to say, WebAssign's going to say, hey, use Simpson's rule with 4, n equals 4 or something like this. But just notice that it's always going to be even. And then error, and then we're done. So error here, what is error going to be? This is going to be equal to the integral a to b f of x dx minus s a b of n. And this is an s. This is not an integral sign. Which, funnily enough, that's actually how the integral, people, wonder about the symbol. Where did that come from? It's an elongated s for sum, right? Because you're summing. But this is a normal s that I'm writing. S a to b of n. Norm here is going to be less than or equal to m. We don't use kappa for some reason in this one. I don't know why. to the fifth, the b minus a to the fifth over 180 n to the fourth. M here is the max over AB of f to the fourth of x. This is the fourth derivative here. Fourth derivative. Okay, what do you notice about this one versus, okay, so I erased trapezoid rule, but look back in your notes. What is the difference? The key difference between these, right? We have Riemann sum. We have trapezoid. We have Simpson. If you look at Simpson's rule, right, this n in the bottom is to the fourth power. Wow, that's so much bigger. This error is going to be going so much slower. So Riemann sum is going to be the easiest to do for a person. Like a computer doesn't care. Easiest to do for a person because you're just doing rectangles. But it, or maybe, okay, maybe I should. It sucks the least. Sucks least. Slowest convergence. What about trapezoid rule? Kinda sucks. And better convergence. Simpson's rule sucks the most. And it is the best convergence. Right? 1 over n to the fourth is going to be going to 0 much, much quicker than 1 over n squared is. And then really, we've only got 1 over n in the Riemann sum. So it's going to be much better. That's the idea. This here is our numeric integration. If you want to do an example on Simpson's rule, it's the exact same thing as trapezoid rule, and there will be the ones on the website that you have to do. If you have any questions, feel free to email me. I hope that you all have enjoyed this video, and I will see you all in the next one. Later.